a rational function? But think of a rational number. What's a rational number? I'll give you a hint. By definition, a rational number when you have A over B, where A and B are integers. Okay, so you have an integer over an integer. So it could be negative 2 over 3, or it could be negative 2 over 1, or 3 over 1, or 1 over 5. So what is this? Fraction. It's a fraction, right? So the rational function, you have a polynomial over a polynomial. So it's basically polynomial that's in fraction form. Okay? It's a rational function. All right? So that was a review of fractions. And so fractions can be decimals too, right? Decimals that and terminate, right? Like 1/2 is 0.5, right? Or repeats, like what's a repeating fraction that's a repeating decimal? Yeah, 1/3, right? Or 2/3, 1/3, 0.3333, right? Or 2/3, 0.666666, right? Those are rational functions that are in decimal form. But for rational functions, I mean rational numbers. But even rational numbers as decimals have a pattern, right? They're either end or repeat. Okay. So properties of rational functions. We're going to find the domain, work on the domain of a rational function, find the asymptotes, the vertical asymptote and the horizontal asymptote, also known as oblique, horizontal or oblique asymptote. Okay, so here we go. Here's our rational function, right? It's our function in fraction form. Polynomial, where P is a polynomial and Q is a polynomial. All right, where Q cannot, where Q is all real numbers except where the denominator is 0. Why? Well, what happens when we get 0 in the denominator? It's what? Yeah, it's undefined, right? Good. Okay. Find the domain. So basically, we said before that for polynomial is all real numbers except 2 cases, right? When x is in the denominator, when x is in the bracket. Well, here we have x in the denominator, right? So so we know it's not all real numbers, right? Because x is in the denominator. So here we have r(x) equals to 3x squared minus 5 over x plus 2. And I'm going to put the other one down here too as well. 2x cubed over x squared plus 4. Okay. Oops, no, this one. All right. So when we have x in the denominator, how do we find domain? Set it equal to 0 and solve. Good. So we put x plus 2. We just put the denominator, right? And so we apply minus 2 to both sides, right? We get, say, so x So what we're really saying here is if we put -2 in, what happens? -2 and +2. Like if we put -2 in here, right? -2 squared minus 5 over -2 plus 2. We get, this will be 12 minus 5. This will be 7 over 0, right? That's undefined, right? So that means x cannot be -2, right? So our domain, if they ask for it in set notation, is x cannot be -2. But if they ask for it in interval notation, then you have to put up basically all real numbers except for -2. Let me see which way they want to do that. So they're asking for it in set notation. So therefore, you just put all values in set x such that, right? And then the curly brackets and you're done, and that's your domain. Okay? Questions there? So they're just asking for it in set notation. So that's a little bit easier. A little bit easier than interval notation. Interval notation, right? Here's -2, and it's basically all numbers except -2, right? So it'd be -infinity to -2, union -2 to infinity, right? But they're not asking for an interval notation, they just want set notation. But that's how different textbooks ask for it in different forms. Okay? So that's why you may see this may seem a little strange because you're used to putting domain in interval notation. Okay, any questions there? How are we doing for time? Okay, we're good. All right, so here, this is a different animal. Because if we were to put this, set it equal to 0, right? What do we do first? -4, right? -4. We can use square root method, right? X squared equals to -4. And then what do we do? Apply the square root. But what happens? It's imaginary, right?
Why would it be imaginary?
Because you got a negative inside the radical. And if it's imaginary, that means it's not real. So if it's not real, that means there is no asymptote. No vertical asymptote. Because if you were to put basically -2 in here, right? -2 times -2 is 4. 4 plus 4 is 8. You don't get an undefined. So there is no number that will give you an undefined in the denominator. And so in that case, this is the one exception where you have the sum of two squares is all real numbers. So the only exception when x is in the denominator, that is, it's not all real numbers, is when you have a sum of two squares, or when you have, even if you just have an x squared, okay, and a number. So this domain is all real numbers, okay, but all right, you may not see that on because I don't like exceptions. All right, I'd rather you solve all of them because you're not going to see this one very much. This one you almost never see. But I had to put it up there, because you may see it sometime, and then you'll know that there is one case where X is in the denominator, and it could be all real numbers. All right. Okay. All right. Any questions with that? Okay. Now, here, using transformations to graph a rational function. All right. Before we get to that, let's do a part, or let's go back to our parent graphs. Okay. And so with y equals to 1 over x, okay, this is a rational function, right? Right? Where we have a vertical asymptote and we have a horizontal asymptote that crisscross at the origin, and then we have two curves. Okay, and then this would be at 1, 1, and negative 1, negative 1. Okay? That's the parent graph. So any transformation that takes place, you have to look at shifting the asymptotes first. And wherever those asymptotes go, the curves will follow. Okay? So if we're looking at y equals to 1 over x, let's say plus 2, okay, that means this is going to shift, this is going to shift up 2 spaces, okay, and so that means this horizontal asymptote is going to go up 1, 2 spaces, and now it's at 2. Vertical asymptote, that didn't change. So the curves, they just ride along those asymptotes. They just follow wherever those asymptotes go. Okay? Questions? Okay. So if we have y equals to 1 over x plus 2 like this, this is like parentheses. Okay? Now that's going to shift. If it's like parentheses, this is going to shift which way? Yeah, left 2. So now your vertical asymptote shifts 2 spaces to the left. The horizontal asymptote doesn't change, but the curve, that curve is going to go wherever those asymptotes are going. Okay? Questions? All right. Now, if you have y equals to negative 1 over x, what do you think that's going to make the graph do? It's going to flip it, right? What was originally up and to the right is now down and to the right. And what was down and to the left is now up and to the left. The asymptotes, they don't change for this one, okay? But it flips that graph, okay? It reflects it about the x-axis. Okay, so we got a couple of minutes still. All right, what? Yeah, we're good. So with this one, r of x equals to 1 over x plus 2. Now this one's squared. So with a square, if you have x squared, right? If this is x squared here, then you don't have a negative side. They're both going up if it's at 1 over x squared. So in this case, this is going to make the graph shift x minus 2. What's that going to do? Which way is that going to shift?
Is it minus 2?
Yeah.
Let's turn it on the left.
It's going to shift right, because it's opposite inside the parentheses, right? Right 2, what's this going to do?
Whoa.
Up 1. So now, this will be right 2. So your vertical asymptote's at 2 and up 1. So now, because it's squared, it's going to behave like 1 over x squared. So when it's squared, they're both up. When it's not squared, one's up and one's down. Okay. So you use the parent graph to start with, and then transformations to shift it from there. Okay, so we'll continue with this on Wednesday. All right.